understand. This is a very complex concept, but it's an important distinction to make because classical computing is very discrete. It's based on ones and zeros, it's binary, and superposition turns these classical states into wave functions so that we can perform unique computation. So, does anyone have any questions about this so far?
I think like one thing that might be kind of like interesting to talk about and like point out is the way that he talks about like we're redefining what a state is here. Like classically, we have this definition of a state being like one or another thing, right? But like according to Dirac, there's like this new idea of like okay, you can think of a state and it doesn't have to be in one or another thing. Like the state itself can be like this is a superposition of multiple things. And so like that's something interesting that like sticks out to me
Yeah.
that like might be worth just like talking about, commenting on.
Yeah, quantum states can be pulled together in a sense. Yeah, it's really cool. Okay, so I'll go on to the next slide. So I have this video, and it's a TEDx video. It's pretty short, it's only like 3 or 4 minutes, but a lot of people are familiar with Schrodinger's cat, and that's kind of an introduction to superposition and this idea of also the dual split experiment, which I'm sure some people here have heard about. But if you guys wanted to watch this video, and it kind of gives a synopsis of it, and I really like the graphics, and it's pretty easy to explain. They do TEDx does a really good job of creating these nice, easy videos to explain a very difficult concept. So if you guys can't hear, just let me know. Are you guys able to hear it? Okay, I just want to double check.
I was unable to hear it.
Yeah,
I can't hear anything.
Unfortunately, I tested this earlier.
Maybe I have to like enable audio in screen share.
Got it.
Let's see. I'm not getting any options on that. Maybe just blast it super loud.
That may work. Yeah, let me just.
Do you think it's because your headphones are in? Oh no, I don't think that would make a difference.
Let me know if you guys let me restart, and then you can hear the TEDx music. Can you guys hear this?
Yeah. Oh yeah.
Austrian physicist Erwin Schrödinger is one of the founders of quantum mechanics, but he's most famous for something he never actually did, a thought experiment involving a cat. He imagined taking a cat and placing it in a sealed box with a device that had a 50% chance of killing the cat in the next hour. At the end of that hour, he asked, "What is the state of the cat?" Common sense suggests that the cat is either alive or dead. But Schrödinger pointed out that according to quantum physics, at the instant before the box is opened, the cat is equal parts alive and dead at the same time. It's only when the box is opened that we see a single definite state. Until then, the cat is a blur of probability, half one thing and half the other. This seems absurd, which was Schrödinger's point. He found quantum physics so philosophically disturbing that he abandoned the theory he had helped make and turned to writing about biology. As absurd as it may seem, though, Schrödinger's cat is very real. In fact, it's essential. If it weren't possible for quantum objects to be in two states at once, the computer you're using to watch this couldn't exist. The quantum phenomenon of superposition is a consequence of the dual particle and wave nature of everything. In order for an object to have a wavelength, it must extend over some region of space, which means it occupies many positions at the same time. The wavelength of an object limited to a small region of space can't be perfectly defined, though, so it exists in many different wavelengths at the same time. We don't see these wave properties for everyday objects because the wavelength decreases as the momentum increases, and a cat is relatively big and heavy. If we took a single atom and blew it up to the size of the solar system, the wavelength of a cat running from a physicist would be as small as an atom within that solar system. That's far too small to detect, so we'll never see wave behavior from a cat. A tiny particle like an electron, though, can show dramatic evidence of its dual nature. If we shoot electrons, one at a time, at a set of two narrow slits cut in a barrier, each electron on the far side is detected at a single place at a specific instant, like a particle. But if you repeat this experiment many times, keeping track of all the individual detections, you'll see them trace out a pattern that's characteristic of wave behavior, a set of stripes, regions with many electrons separated by regions where there are none at all. Block one of the slits and the stripes go away. This shows that the pattern is a result of each electron going through both slits at the same time. A single electron isn't choosing to go left or right, but left and right simultaneously. This superposition of states also leads to modern technology. An electron near the nucleus of an atom exists in a spread-out wave-like orbit. Bring two atoms close together, and the electrons don't need to choose just one atom, but are shared between them. This is how some chemical bonds form. An electron in a molecule isn't on just atom A or atom B, but A plus B. As you add more atoms, the electrons spread out more, shared between vast numbers of atoms at the same time. The electrons in a solid aren't bound to a particular atom, but shared among all of them, extending over a large range of space. This gigantic superposition of states determines the ways electrons move through the material, whether it's a conductor or an insulator or a semiconductor. Understanding how electrons are shared among atoms allows us to precisely control the properties of semiconductor materials like silicon. Combining different semiconductors in the right way allows us to make transistors on a tiny scale, millions on a single computer chip. Those chips and their spread out electrons power the computer you're using to watch this video. An old joke says that the internet exists to allow the sharing of cat videos. At a very deep level, though, the internet owes its existence to an Austrian physicist and his imaginary cat.
That was great.
So, I just thought that video is kind of gave a. It's basic and but at a basic level gives an understanding what superposition is, especially from a physics standpoint, which from a computer science standpoint may seem a little different, and that may have gotten a little bit wonky with regards to like the quantum chemistry and the position versus speed, wavelength, all that kind of physics jargon. But the essence of it, for me at least, is that with the dual split experiment, you can think of the electrons when they just go to a singular position. That is like a classical computer. And when you do the dual split experiment and you actually measure the state of the electrons, that's what happens. They act as normal classical electrons, and they just go through one of the two holes, and they don't act like a wave at all. But when there is no measurement, these electrons act in a quantum state. And as you can see, they hit the screen here as a wave function. So it's as if they go through both the slits at once. And we use this superposition to our advantage in quantum computing, because with qubits, you can put bits into a superposition and then perform unique computations on them that you couldn't unless they were in superposition. So does anyone have any further discussions or questions regarding this?
I don't know that it's central to the underlying point you're trying to make, but the video seems to imply the electrons go through both splits, but that's not necessary for the exercise to succeed. An electron beam gun doesn't fire one electron at a time, so you end up getting electrons going through both slits. It's just that they interact with each other in ways that are, well, weird.
Yeah. From what I know about, I'm not a huge expert in the dual slit experiment. But yeah, from what I read, it's, they're firing millions of electrons, and the pattern that appears on the screen is a wave function. It's not that the electron splits off and then forms two. It's just the way the quantum states behave ends up with this pattern on the screen. And moving on from this, kind of like I said, with classical bits, it is electrons acting as straight particles. They don't split, or they don't act in these quantum states to form these wave-like properties. But with quantum states and qubits, that's exactly what we rely on. So what we do is we create these qubits and we chain them together through tensor networks. and through and then we put them into superposition using a certain type of quantum logic gate called a Hadamard gate. And what you can think of it as, you can think of two separate waves that then form together to form a bigger wave in a sense. And you can perform computation on this bigger wave to do some really neat things that are kind of a little bit difficult to describe, but I can get into here in a little bit later. But kind of the basic concepts of this whole superposition stuff is that quantum states can be added together into superposition. These states act as wave functions, and this phenomenon allows us to perform unique computation. I think the end got cut off there at the end. Any questions regarding this?
I think like one kind of like example that might help like enlighten a little bit of what this is trying to illustrate would be like to directly speak towards like the types of problems that we can accomplish and hope to achieve with like a perfect quantum computer or qubit. So like if we have some function f of x, right, or some like set of linear functions that we would like to compute a solution for, well, there's like generally a few different ways that we can do that, but a naive way would be to try every possible solution to this like set of linear systems, right? Or this like even singular function that we need to find a solution for. In a classical machine, we don't have this property of superpositions. We don't have this property of being able to like put states together and then like do funny things to those states. No, it's the case that you actually just have to deal with definite states. You have to deal with trying 1 and trying 2 and trying 3, et cetera, et cetera. But with a quantum machine, that limitation is taken away, at least theoretically. You have the ability under superposition to put multiple states into a combined superposition that can then be computed upon and treated as a single state. So what I mean by that is like, if we wanted to try the numbers 1 through 5 as solutions to our function, classically we try 1, we try 2, we try 3. But under a quantum machine, knowing that we have superposition, we could actually just take these 5 states and superpose them together. Upon that newly created superposed state, we can just check if the function has that solution as a whole. And now like it's a little hairier than that, because you don't get to just say, okay, I'm going to try all these states at once and like, let's see which one works. No, like at the end, you still have to come back to classical reality. You like, it's not all sunshine and rainbows under superposition, because at the end of the day, we don't see cats in like the state of being dead and alive. That whole like point that was illustrated of like the hour expiring and it is now at one state is due in part to, well, exclusively to measurement. And so like at the end of the day, there's funky things that we need to do and to be clever to like find the answer that we want, but like we still get a little bit of a kind of a cheat code in a sense, because at one point during computation, we do get to take advantage of superposition, and we do get to compute on multiple things and try multiple solutions all at once. And like it's not as simple as that, but that is like something that we can gain from superposition in quantum computing.
All right. If anyone has anything else they'd like to just point out, any questions at all, like they took, some quote from a famous physicist. I think it may have been Einstein or maybe Dirac, but he was the more you think about quantum mechanics, the less you understand it. And these are very hard concepts, and I still can't fully grasp my mind around them. But yeah, it's awesome they're really interesting, cool to talk about. So if anyone has any questions or just comments or anything, feel free to just chime in.
So I'm again trying to get my brain around this because it's bending me a little bit. But is this in theory at least similar to a single instruction, multiple data vector processor we might have in a conventional computer, where we're effectively throwing the same operation at multiple different pieces of data at the same time, but just with one qubit?
Yeah.
Yes, similar to that. Probably the best. Sorry, Teddy, if you want to
Go ahead. You got it. You got it.
Thanks. It's really interesting. Probably the best example I could think of a quantum computation is this thing called a quantum Fourier transform, which is where you have so you take all these quantum states, tensor them all together, and using a Fourier transform, you're able to kind of the positive, this is going to sound weird, but like the positive and the negative answers kind of collapse into each other using the quantum Fourier transform. And you're able to see exactly what is the biggest spike in the probability. And here in a little bit, we're going to get into how these qubits can be represented as probability density functions, which I think clears up a little bit about how this computation really works. But yeah, there's what kind of the consensus right now is you have qubits, and they kind of act as classical bits, and then you put them in superposition and put them in these quantum states, and then by measuring them, kind of like when you measured electron in the dual slit experiment, it collapses into a particle, and our particle in this case is a classical bit. So you take classical bits into quantum superposition states, fool around with some computation, and then you can collapse them back into classical bits, and that's how you get quantum speed up. That's how you get a lot of the exponential speed up of. That's why they say quantum computers can solve problems way faster than classical computers.
So is there a theoretical limit to how many states you can put into a superposition at one time?
Not that I believe. From what I hear, it's just infinite.
So
yeah, Teddy. Yeah.
The problem, like, it is not like a theoretical one. Like, in theory, it is possible to construe an infinite amount of quantum states. The tricky part is, like, okay, we can make quantum states, but then we have to control them. We have to manipulate them. And controlling and manipulating quantum states is, like, vastly more difficult than classical states. Because if you think about it, like, we have these, like, superposed states, and in a quantum view, everything is kind of like wave-like, and like the probabilities are like the actual kind of manifestation of reality, and all these things kind of like interact with each other. And so have, like, in a nutshell, to not go like too far down that rabbit hole, noise from the environment is extremely inhibiting to how many operations you can do on a system of qubits. And so, like, theoretically, we can kind of superpose qubits over and over and over and over and make like this infinite amount of like superposition states. But like after a certain threshold, you get like more noise and more interference. And at some point, it's like you're just playing around with a random system or state generator. It's not even like anything reliable or anything that like is a Turing machine in any sense at all. It just becomes a random number generator.
Yeah,
that makes sense.
Yeah. So yeah, and then just going off what Teddy, classical bits just you have 1 and a 0, and if you have a little bit of electromagnetic radiation, like a positron or something, affect these two states, you're going to get a little dip in like the electromagnetic reading of the bit, but it's still going to be above the middle threshold enough to be registered as a 1. But since a quantum computer has to be a perfect wave function, even a little bit of interference can screw up your whole computation. And that's why quantum computers are usually, at least superconducting ones based on superconducting elements, are kept at near absolute zero temperatures. That's why they talk about IBM has a great video on YouTube explaining their quantum computer and how it's a big refrigerator, because they want as little noise as possible affecting this quantum state, because if they just get one electron into their quantum state, it'll screw up the entirety of their wave function, and they'll end up getting a result that is not what they anticipated, and then it's useless, because a computer, they want it to be a perfect cause and effect machine in a sense. Yeah.
Okay.
Awesome. Anybody else have anything they'd like to chime in?
So once we measure our quantum superposition, how do we retain the quantum information once it snaps back to the bit?
Well, so there's actually like a few different ways to quantum compute. The way that we're talking about right now is pretty much you have classical information that you put in a quantum state, and then you get back to a classical bit. So you essentially don't want to retain any quantum information. You just kind of want to use the quantum mechanics to perform calculations faster than normal. Does that kind of make sense?
One thing that like might help, like if we think back to that video of Schrodinger's cat, like, okay, the hour is up and then you open your box and your cat's either dead or alive. Well, like, can we make that cat like go back into being dead and alive? Like, no, that's bizarre. I mean, I don't know a way to do that. Like, that would be like bring this cat back to life if it was dead. The whole like idea behind superposition and like quantum representation, or a huge idea, is like the fact that quantum information can't be retained. It fundamentally should not and cannot be retained, because like upon measurement you're actually like bifurcating the state to like be realized into something, right? Like that cat's either dead or alive after an hour is over. Before that, like we can talk about a quantum view of the cat, but like after that, like there's no way to say like, okay, let's like put that back into, or like figure out something about the quantum state of that. Like it has no quantum state at that point, at least in that respect.
I believe that there is quantum, like other forms of quantum computation that actually take in quantum data, like quantum experiments, and then it retains quantum. The output is also quantum data, but for this case scenario, we're kind of talking about classical applications of quantum computing for computational speed up. Does that kind of make sense?
I guess I was just kind of confused, like how that quantum processing like gets to that classical. Like for example, I heard that quantum computing helps solve like passwords and stuff. So does it like try every possible, or not every, try many possible solutions, and then gets back that password?
If you want so that's Shor's algorithm, which is a really fascinating algorithm. And that actually uses a quantum Fourier transform, which I mentioned before. I could send you a link to I think it's like a 10-minute video that explains exactly how that happened. It's by, have you heard of Minute Physics?
Yeah.
Yeah, it's a Minute Physics video explaining Shor's algorithm for RSA encryption and how exactly the quantum computer can break that down. And what that is Minute Physics does a really good job of explaining that better than I ever could. So if you want, I could post a link in the chat right after this presentation, and then if you want an idea of how that works, just watching that video will clear everything up. I almost guarantee it.
Yeah, that'd be great. Thank you.
Yeah, of course. And then but the Minute Physics video with regards to that can deal with the next thing, which is So that deals with the probability density function, which I'll kind of get here in a minute. So like we mentioned before, the applications of quantum superposition and this stuff to quantum computing is that we can turn our ones and zeros into superposition states, which is This is Ket and Bra notation right here is what you're seeing right here and right here. Can you guys see my mouse, my cursor?
Mhm. Yeah.
Okay, cool. And what we do is we take these states and we tensor them together, which is putting them in superposition, so that we can, well, tensoring together, we're actually just combining the states, and then we do this thing called a Hadamard gate, which then puts it in superposition. But what these do is they act as, these matrices essentially act as a probability density function of which state it's going to collapse into. So right now you're looking at so you have 2 qubits and there's 4 possible states when you tensor them together. You have a 0, this right here is the first bit, and there's a 0% probability that it's going to collapse to the first bit. There's a 100% probability it's going to collapse to the second bit, 0% probability it will collapse to the third bit, and 0% probability it will collapse to the fourth bit. So by tensoring these together, we essentially turn qubits into a probability density function matrix. And the more qubits that you have, this matrix gets humongous because it's exponential. So if 2 squared is 4. And then 2, if we had 3 qubits, this matrix would have 8 possible states. 4 qubits, 16, 5, 32. Eventually, when you get to 30 qubits, you're in the billions. And when you're at 100 qubits, that's more, I think it's like more atoms than there are in the universe. No, it's not that high, but I think that's when you get to 1,000, my bad. But this is where we see the exponential speed up with regards to qubits. With such a small amount of qubits, you can represent more states than all of our computers combined, which is where you get, that is where we can solve some of the most perplexing problems in computer science, like prime factorization, which is the password breaking that you were talking about, Aaron. That Shor's algorithm breaks the prime factorization of that RSA encryption is based off of. And then another big one is a traveling salesman problem, which is if you have this guy and he's got to visit 30 cities, what's the fastest route he can visit all the cities? And it takes a large amount of computing power to figure that out. Highly recommend that. If anyone's interested in this, highly recommend looking it up. Yeah. Any chime-ins? Any questions, concerns?
Yeah, could you go over tensors a little bit? I'm not too familiar.
Tensors are a Teddy, do you want to get a crack at this potentially?
Yeah, so as opposed to the matrix product or the dot product where you do like columns times rows, what you're doing here is you're doing an element-wise multiplication. And so like we've got these 2 vectors, 1, 0 and 0, 1, right? Which are, I wish you guys could see my mouse, but they're like the green and the blue, right? After the second expansion of that expression. Yeah, so like what we're doing is like element wise, we are multiplying. So we take element 1, 1 or 0, 0 of the first vector and multiply it by the entirety of the second vector. And so like it's just a little different from dot product. It's like, it's weird. It is like, we'll probably take some getting used to, or at least like playing around with it a few times. Yeah. But like I think what might be more important is just like the motivation for this. Like we want to be able to, what is being represented here is not like, it's not the state, it's the probabilities of like the states, right? And so what I sent in the chat is like, these are the possible states. So it goes like from top to bottom. We're saying that these are aligned. Think of this aligned with that the result of this expression. That 0, 1, 0, 0. So the probability of getting 0, 0 as described by my message and then like in here is 0. The probability of getting 0, 1 is 1. The probability of 1, 0 is 0 and 1, 1 is 0. So like there's kind of this implied like table of like the possibilities for the actual states that goes along with this. But like that's kind of something that we can just like, that's very simple, that's trivial. Just expanding this, like if we were to go to 3 bits that we're like representing in one system, then like we would start over, and first it would be that, and then it would be that, and then et cetera, right? This would keep expanding, and it's implied as to how it would expand. But what's like interesting, or what's like important, is not this, but like the probabilities. Because like we know that if we put 3 bits together, then like there's 9 possible combinations that we can get. But like in terms of measuring this, yeah, there's 9 possible combinations.
I think you mean 8.
8 possible combinations. Yeah, thank you. But we're only going to measure 1. And so what this like tensor is depicting is the probabilities. So it's like probability 0, and then 1, and then 0, 0. And you're only going to have like the sum of that is always going to be 1. Because like,
oh yeah,
these go to 100.
The sum of this final matrix is always going to be 1, because it essentially, this matrix can be represented as a probability density function, which if you take in statistics, I'll go over it here in a second, but just don't worry about tensors too much right now. They're kind of weird, and just think of it as like a little bit beyond linear algebra. If you know matrices, they're just a little bit more complicated than matrices, but it's kind of how we represent qubits. But yeah, don't sweat too much on it right now. That's kind of something we can go into a lot deeper later. But yeah, so then we got the probability density function, which is this is what this last tensor is being represented. It's kind of like this graph. If you see, the area under the curve is equal to 1, because we have a probability of certain things collapsing to certain positions. I couldn't find a graph that had the exact axes I was looking for. So assume instead of -4, -3, -2, -1, 0, and whatnot, just assume this is position bit 0, 1, 2, 3, 4, 5, 6, or 7, just like a classical computer, just like you have a few bits. But so what we have is we have our qubits, and we tensor them together. We put them into superposition, and then so what happens is when we have our superposition, we put it essentially into a wave function, like a probability density function, where there's maybe a 50% chance that our qubit is going to collapse to the number 3 when we measure it, which would be, 0, or that would be like 1, 1, 0, 0, essentially. Because this is like, sorry, I went too far. I assume like this is bit 1, or bit 0, this is bit 1, this is bit 2, and this is bit 3. Right now, there's a 100% chance that I might collapse to bit position 1. So that's kind of how it goes. There's a probability of certain bits collapsing to certain things. And with quantum logic gates, we're essentially affecting this probability density function, and we're amplifying certain things because we want stuff to collapse to certain bit positions based on our problem. And that's getting into quantum algorithms, which is a little crazy. But yeah, we have our qubits, put them into superposition, perform some computation, measurement, and then they collapse to a certain position, if that makes any sense. Does anybody have any questions? This is some heavy stuff, completely understand. I may not be doing a fantastic job explaining it, but yeah. Any questions, concerns? Okay. I think what I had was I had another, this video is a little bit longer. I may skip to like the 3-minute mark. It's like 7 minutes, but this is a Kurgenstein. I can never pronounce it. It's German, I think. But they do also really good at infographical videos and how quantum computers works, if you guys would be down for watching it. And it's just got a few minutes left.
History, human technology consisted of our brains, fire, and sharp sticks. While fire and sharp sticks became power plants and nuclear
I will skip
and making things true, which is a passage that can block electrons from moving in one direction. Today, a typical scale for transistors is, for most of our history,
very sorry.
8 electrons move and tinier, quantum physics are making things tricky. In a
Right here, the
nutshell,
good part.
a transistor is just an electric switch. Electricity is electrons moving from one place to another.
And just to clarify, transistor is like a bit, computational bit.
So a switch is a passage that can block electrons from moving in one direction. Today, a typical scale for transistors is 14 nanometers, which is about 8 times less than the HIV virus's diameter and 500 times smaller than a red blood cell's. As transistors are shrinking to the size of only a few atoms, electrons may just transfer themselves to the other side of a blocked passage via a process called quantum tunneling. In the quantum realm, physics works quite differently from the predictable ways we're used to, and traditional computers just stop making sense. We are approaching a real physical barrier for our technological progress.
And this is a big push for quantum computing as transistors get smaller and smaller and smaller, which is the ability to store a bit as a 1 or a 0. We're reaching a physical limit to that. And that's why everyone's pushing to quantum computing, because it is like how we are going to further progress the evolution of computers, because they're about to kind of cap out, at least how small we can get transistors, which is, that means your phone can only get bigger because you're going to have to start adding more memory to it, which is no fun. Yeah.
To solve this problem, scientists are trying to use these unusual quantum properties to their advantage by building quantum computers. In normal computers, bits are the smallest units of information. Quantum computers use qubits, which can also be set to one of 2 values. A qubit can be any 2-level quantum system, such as a spin in a magnetic field or a single photon. 0 and 1 are this system's possible states, like the photon's horizontal or vertical polarization. In the quantum world, the qubit doesn't have to be in just one of those. It can be in any proportions of both states at once. This is called superposition. But as soon as you test its value, say by sending the photon through a filter, it has to decide to be either vertically or horizontally polarized. So as long as it's unobserved, the qubit is in a superposition of probabilities for 0 and 1, and you can't predict which it will be. But the instant you measure it, it collapses into one of the definite states. Superposition is a game changer. 4 classical bits can be in one of 2 to the power of 4 different configurations at a time. That's 16 possible combinations, out of which you can use just 1. 4 qubits in superposition, however, can be in all of those 16 combinations at once. This number grows exponentially with each extra qubit. 20 of them can already store 1,000,000 values in parallel. A really weird and unintuitive property qubits can have is entanglement, a close connection that...
We'll talk about entanglement later, but I just thought that video did have kind of a better job explaining the importance of quantum computing. But yeah, that's all I really had for this presentation. Do you guys have any questions, concerns, ideas?
So far, so good.
Awesome.
Awesome. So
Well-
I am going to be doing an intermediate lab in 15 minutes, same Zoom call. If you guys want to like go grab some water or like whatever, take a 15-minute break. I encourage everyone, like it's called the intermediate lab, but it's really not very much more complicated than this. And much of what I'll be talking about builds like specifically off of superposition. So like having it fresh in your mind will be perfect if you're interested in hanging around.
Yeah. Sounds good. Thank you guys so much for coming. We hope to grow these meetings over time and delve into some cool topics. But yeah, thank you guys so much for coming. And
Thank you both.
see you in 15 minutes if you guys want to stay for the intermediate lab. Awesome. All right. I'm going to hop off the Zoom call real quick, Teddy. I'll be back on
Yeah,
it in
you
like
got
10
it,
minutes.
man.
Thanks, man. How do I stop the share? There we go.
I think that might have kicked you off because I just
Thank
started.
you.